Okay. I don't know if you got any alerts, but it looks like we are recording now. So let's go back to the share here of the practice test. So definitely, bring a calculator with you just in case. You'll be provided a periodic table as always. And of course, I'm there if you have any other questions. But this first question, this is back in chapter 6. So what we need to consider here is the electromagnetic spectrum, right? So we looked at some different types of radiation, some types of, such as ultraviolet, microwave, X-ray, infrared, or radio waves, including the visible spectrum as well. So you might have this memorized, but if not, X-rays here, can I highlight? X-ray is going to be our correct answer because of the correlation between energy. Let's see if I can write here. Between the energy and the wavelength. So right? We remember this equation, energy equals hc over lambda. So the smaller the wavelength, we would see that X-rays have the smallest wavelength, and then also they have the highest frequency. So because of those two reasons or those two properties of X-ray radiation, they have the shortest wavelength, right? We can relate that to wavelength. We can also say they have the highest energy. So this next question kind of ties into that, the ionizing radiation. I mentioned how ultraviolet, I think I mentioned this in class, but ultraviolet right next to the visible spectrum,
Yeah, I
right?
have a question. Wait, I have a question. My bad for interrupting.
Oh, yeah, sure.
So those equations are number one. Would that be on the exam too tomorrow?
It could be.
Okay.
Something using this equation could be.
All right.
Mhm. So these are the only two equations from chapter 6 that are coming to mind. Um, So I would know these equations. I would know where different radiation is placed on the electromagnetic spectrum. So ultraviolet, we discussed, was also an ionizing form of radiation, but it's not on this list. So the only one here that has high enough energy to be considered a dangerous or ionizing radiation, as was mentioned in the textbook, would be X-rays. So far we have C and then E. All right. Let's see what happens if I scroll down here. Okay, perfect. All right. So sometimes questions are, just conceptual or definitions. This question here, we have to kind of think all orbitals in a given subshell. So first we think about what's our shell, right? So that's the period that we're in. Our N is our main shell. And then within a shell, right? So say we have an N, I don't know, equals whatever I can write here. All right. So say I have an n equals 2. I need a larger space. Within that n equals 2, right, my second shell here, I have the 2s and the 2p orbitals. So these are two subshells, right? And that's what we're asked about here. And they both have the same what, right? What quantum number? The principal quantum number. S will have a different L value than a p orbital. So the only quantum number that's the same is the principal. All right. So that was answer A. Um, so sometimes we were asked what are acceptable quantum numbers. Sometimes we're asked what are unacceptable quantum numbers. This question asks kind of somewhere in between. It asks us to interpret which quantum numbers do not exist due to constraints on angular momentum. So that would imply, due to the equation or the way that we figure out angular momentum, our m sub L, right? Which of these, oh, I'm sorry, our L value rather, gives us our shape, right? Depending on how we figure this out, some of these orbitals cannot exist. So we know that the equation for L, right, is 0 up to dot, 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 n minus 1. Right, so we start at 0, that's an acceptable L value, and then we go up to n minus 1. So for, let's see here, another way of looking at this is just that fact that if we remember, in the second period, we do not have any d orbitals. That's a dead giveaway as well. But we can arrive at answer choice C by memorizing that and knowing that we don't have d orbitals till period 3 or beyond. But we also could say if I have an n of 2, I can only have an L of 0 or 1. And right, because we only go up to n minus 1, and that would only be for an s or p orbital. So that's another way that you could figure out that we do not have this d orbital in period 2. So if our n is 2, we cannot have an L of 2. All right. So I'm going to keep going until anybody says, any questions.
Wait, it's not none of the above.
What's
Because we have D and we use like one like S, P, and D. So how is 2D not the 2D the answer?
So 2D does not exist. The others can exist. Yeah, so 2S can exist because we can have an L of 0 with an N of 2. 2P can exist because we can have an L of 1. Remember, an L of 1 is for P, L of 0 is for S. But we can't have an L, which gives us the angular momentum, the shape,
Yeah.
of 2 with an N of 2 because we stop at N minus 1.
All right.
So what about number 5 here? This one, let's check and see if any of these do not exist, cannot exist. So it's the same exact question. We just have a different n value here, right? So now we have n equals 4. Oh, it's supposed to be an equal sign. It's doing something weird. Here we go. So n equals 4. So we can think about angular momentum here. What L values can we have? We can have 0. So that's an S. We can have 1. That's a P. We can have 2. That's a D. I can have a 3. That's an F, right? I can have S, P, S. Oh, sorry. This is not helping. P, D, or F here. Okay, so we can have any orbitals. So any of these are possible. So I'm going to uncircle that and say that the correct answer choice would be E, that none of the above we can say do not exist because of angular momentum constraints. All right, so again, just follow that rule. N can be any whole number integers greater than 1, so or 1 or greater. So N could be 1, 2, 3. L's can be 0 up to N minus 1. And then here we're going to look at the rule for M sub L. Hmm. Along with the rules for N and L here. So we know that n is any number great 1 or greater. So any of these n values are acceptable. When we get to our L value here, we know that our L cannot exceed our n. So it looks like all of our L values are okay as well, right? So 2 is less than 3. Oh, did somebody send me a message? Hold on. No, I think somebody just joined. Sorry, guys. Let me go back to the share. I thought I heard messaging. Okay. All right, it should. You are screen sharing. I'm sorry, guys. I can't see the screen share. Let me switch. Here we go. Okay. So we're back. So in answer choice A here, we've confirmed that our L doesn't violate, right? It's less than our N. Okay. And we see here our L doesn't violate B, so that's good. C, definitely not, right? It just has to be at least 1 less. So all of these check out up to the L value. Now let's confirm our M sub L. Remember the M sub L, the rule for that is that it can be all positive or negative values of L, including 0. So if you have an N of, I'm sorry, an L of 0, for example, you can only have an M sub L of 0. But if I had an L of 1, I could have -1, 0, or 1. So in that scenario, we can see that A here, we cannot have a positive or -3 because my L is only 2. So I'm limited to -2, -1, 0, +1, +2. So for 6, we would pick answer choice A because the M sub L violates the rules. So orbital notations here. So d orbitals come into play in the third period. So the earliest that we see d orbitals would be 3D. So we will not see f orbitals, and I told you you won't see these on the exam, but for the purposes of this practice test, we won't see f orbitals until the fourth period, right? So after the d orbitals, we would start filling those. But all of these look good, right? We have an s orbital in 4, an s orbital in period 2. We would have d orbitals available in period 4, and we would have p, x, y, and z orbitals all available in period 3. So it looks like since we don't start f until period 4, d is the correct answer here. But again, I'll repeat, you will not see much, if anything at all, about f orbitals on the exam. When the X and Y are down there in Z. Oh, so that's one of the 5 possible d orbitals. So we ran out of just X, Y, and Z coordinates. So that's one of the, if you look up all 5 of the orientations of the d orbitals, that's one of them. So see here, it's wrong, sorry, but that's what the XY means. All right, and then let me know if that did not help. So I'm going to keep going. But yeah, there's 7 different orbitals for F, which you definitely do not have to memorize. There's 5 for D, which you won't have to memorize. Just know that S, there's only 1, right? And then P, there's the X, Y, and Z. Oh, I don't want to indicate any of these individually because we're asked here which orbitals or orbital, right? Orbital or orbitals can hold 2 electrons. So say we're in an s orbital, right? We know we can hold 2 maximum, but it can hold 2 orbitals, 2 electrons. Then we have our p orbitals, the x, y, and z. Each individual p orbital, the px, the y, or the z, remember, it can also hold 2 electrons. So we have here for number 8, all of the above, right? All of the above orbitals can hold 2 electrons. Right, so D here for answer choice 8. All right, and let's take a look here. Number 9. So here we're going to eliminate which cannot exist, right? What's a not a valid set for the 4 quantum numbers, and they're always going to follow this order. So N is first, then L. Oh, I won't number them. So N is first, then L, then M sub L, then MS. So let's take a look and see if these follow the rules. I don't see any N's that are less than 1, so we'll move on to our L column here. So the rule is that the L goes up to n minus 1. So when I get to B, I find a violation, right? Because if my n equals 1, that means that my L can only equal 0, right? And that means that in period 1, we only have an s orbital, and that makes sense. All right, so 9 was B. Let's take a look at 10 here. Okay, electron configuration. So this is way back towards the beginning of this unit as well, or these units. So we want the ground state. You will not be asked for anything beyond that. Where do we see? Which question is that? 5S1. For this here? Oh, yeah. So this is because this is one of the exceptions to the rules, which you will not see an exception. But when we half fill a d orbital, the atom or the electron configuration is more stable than if we fully fill the s and then only have, say, 4d4. But if we half fill, so 5 out of 10 here are in this orbital, it's more stable than if it was 5s2, 4d4. But again, this is one of those many exceptions to the rule that we're only going to see the rule on the exam. So you would fill this, as normal on the exam, right? So you would just fill the 5S first, and you probably won't have D to worry about. But again, this is one of those exceptions where if we half fill the D, I'm sure this was mentioned somewhere in the textbook, it's more stable. So this would give us 6 electrons after chromium. So if you don't have a periodic table handy, let's take a quick trip because I do not have mine handy. So we need 6 electrons after chromium, right? Or krypton, I'm sorry, krypton. Let me share what I'm looking at with you guys here. Okay, so we were told we have that we have krypton, then 5s1, 4d5. So we know that we're going to be 6 electrons after krypton. So we go krypton, and then, oh, this is not the best. I'm noticing here. All right. And then we have 1, 2, 3, 4, 5. Um, 6 here if we move over. So molybdenum is going to be our answer here. So E, let me go back to the exam here, but I'm going to show you one more time. So we start at krypton 36, and then we count over 6 electrons. So 1, 2, 3. This periodic table is kind of split in half. 4, 5, 6, until we get to molybdenum here. So this is answer choice E. Let's go back to the other document here. Sorry, I'm not sure if it follows me or not. So we're going to reshare. Okay. All right. So all you have to do is count, right? 6 electrons past whatever noble gas, and then that's where we end up with the correct element. So it was like 36 plus 6 more got us to number 42. All right. So when we talk about these types of atoms here, these are only in period 2. We won't see any tricky d orbital half-filled things with nitrogen or even oxide. But nitrogen, this is our neutral atom. So again, if you have your periodic table handy, you would see that nitrogen's in group 5, and it ends in the p orbitals. It's the third element in. So using our periodic table, we would go over to where nitrogen is, and we would expect to end with 2p3, right? Because we are in group 5. And we can see that in our second shell here, we do indeed have 5 valence electrons. So this would be answer choice C for number 11. So again, the periodic table is the best place to find help, to find answers for electron configurations, even for ionic electron configurations here. So the oxide ion. So first you have to figure out what that is. So that's oxygen with two extra electrons, right? Let me try again. Oh, 2 negative is the oxide ion here. So we go to oxygen, which is in group 6, and we expect that to end in 2p4, right? So if you have your periodic table handy, group 6, for oxygen specifically, our last electron that we would fill would be 2p4. Now that we're adding 2 more electrons, we know that ions form to gain stability to become like the noble gas closest to them. So the oxide ion would gain 2 more electrons, and we would end with 2p6 here, right? So it would gain its stability, it would get its octet, and its oxide's electron configuration is down here, letter E. All right, so that is think most of the chapter 6 type of questions that you might see. All right. So I'll pause for a second. Any questions about that type of stuff? Right. Remember, you will have a periodic table, you'll have a calculator handy. I think that's more than all you'll need.
Question: does
Mhm.
C equals 2.998 or to the eighth power or 3 to the eighth power?
If you use either of those, you will get the within the right answer choice. Like you'll be able to tell. So he's asking what's the speed of light constant, 2.998. times 10 to the eighth, right, meters per second, or just 3 as your coefficient. So again, if you use either, you're going to get the same, within the same answer. The
Uh,
answer choices won't be that close that they're off by like a 10,000th or something.
okay, thank you.
You got it. All right, so let's look at 13. I almost skipped 13. All right, so number 13, we're asked about increasing polarity. So we're going to think about the least polar to the most polar here. All right, so what do we have here? So we want to think about the difference in electronegativity. So this is where you would look at your periodic table and you would say, all right, well, fluorine I know is the most electronegative atom. So whatever atom is furthest from fluorine would be the most polar bond, right? So I'm looking between oxygen and fluorine here, nitrogen and fluorine. These are all very close on the periodic table, all these last four choices, B through E. But magnesium is a metal, right? It's all the way in group two, so it's on the other side. So that's kind of like a shortcut where you can zone in and see what's the greatest difference in electronegativity. That will be your most polar bond. So again, it's just proximity, distance on the periodic table, right? So you'll have everything you need. And these atoms, there's really not much ambiguity here, right? We could tell which ones are close to fluorine, which ones are far away. Right. And then we can kind of confirm these are in order. So beryllium is almost as far as magnesium, nitrogen's a little bit further than oxygen. All right. So number 14, which is considered nonpolar. The only set here of atoms in the bonds, they're all covalent bonds, but the only one that's considered nonpolar, which this is less than a difference in electronegativity, so less than zero point 0.5 difference would be this CH bond. So you're not expected to memorize numeric values, but you are expected to know that this is the only nonpolar covalent bond. And since it's on the practice test, you may not be asked that specific question again. But still know if you're asked about, say, which are polar bonds, that CH would not be in that list. All right. So don't lose that information, but you won't
Quick
see
question.
it presented.
Wait, how do you know which, if that question is asked for a test, how will you know which one's polar?
All bonds will be polar except for CH or the same atom. So, for example, like an NN molecule, right? So, this is the Lewis structure for the diatomic nitrogen. So, any diatomic and CH polar, CH covalent bonds would be nonpolar. All other covalent bonds have some associated polarity.
Okay.
Hmm? Resonance structures. Okay, so we've looked at these and we had to make some decisions when we were doing our Lewis structures as to if we needed to create a double bond or even maybe, probably just the double bonds we saw where we had to make decisions. We could create what are called these resonance structures, which are two, if you remember, like incorrect representations of an atom. So, oh, sorry, that one's really wrong. But this one's ozone, right? Where we two, sorry, there's a lone pair supposed to be on top of that oxygen. And then we have the other resonance structure over here, which we know is also an inaccurate depiction where we just choose the other oxygen-oxygen bond to be a double bond. So the only difference between these is the placement of electrons. If we had different atoms, the atoms would stay where they were, but we could move the bonds. So that implies moving electrons, right? And we can also make lone pairs if we wanted to, but it's still going to go back to placement of electrons. So the only thing that can change. All right, the number of electrons is always the same, and the number of atoms is always the same. So all of those are the same except for where the electrons go. All right, oxidation number. So this is thinking back, right, to I don't know, chapters 4 or 5, around there, when we looked at redox reactions. So remember, if you uncross your charges here, right? So oxide we know is a -2 charge. Ooh, so our iron must be +3, right? I just uncross my charges here. Let's see here. So the central atom in I will give you guys the correct answer and explain why. Carbon cannot do the expanded octet. So I would start with this and do this Lewis structure first when I'm asked about octet violations, because I know that all of these central atoms can accommodate more than an octet because they're in period 3 or below. And then if we did the Lewis structure for the four that are underlined here, the four wrong answers, we would see that each of them, the central atom does violate the octet. So I would look for an atom that cannot do that Lewis structure and confirm, and then maybe go back and check if you're still unsure. All right, so look for some shortcuts, right, when we can't violate the octet rule in period 2. Let's see here. So a similar question for 18 here. But in this case, it says which one cannot be drawn without violating the octet rule. So in this case, um, I'm going to say, well, something that has more than 4 bonds by default, right, has to violate the octet rule. So ICl5, iodine, pentachloride here, this will have 10 electrons surrounding iodine at least, right? And if we might find out there's a lone pair that we can't predict without doing the Lewis dot structure count or the valence electron count. But we definitely know it's at least going to have 5 bonds. So we can shortcut and say this definitely needs to violate. All right. Any questions about octet rule violations, things like that? Period 2, below period 2, so carbon, nitrogen, oxygen, none of those can do the expanded octet.
Can you explain 17 again, please?
Oh, yeah. Let's see here. So I would start. So we were asked which one does not violate the octet rule. So I looked at my central atom. So we kind of have a feeling now, due to symmetry, what's our central atom going to be, just looking at the formulas. And the only atom that cannot do an expanded octet is carbon. Um, I don't know where my eraser is, but answer choice B there, carbon tetrafluoride. I would start there with that Lewis structure, confirm that it doesn't violate the octet rule, and I could move on with confidence, but that's why I started there with the carbon tetrafluoride, because carbon cannot do the expanded octet. All right. So let me know if that didn't
Okay, thank you.
that answered. Okay, cool. All right.
Sorry, could you please repeat the explanation for 16?
16.
Yes.
So this is back with ionic compound formation. So our formula is Fe2. Let's see if I can just remove some stuff here. So I'm going to uncross my charges, remember? Because when we look at the individual ions, so O2 and whatever iron is, whether it's 2 or 3, they become the subscripts, right? Because we know that we need, 2 times positive 3 to equal 3 times negative 2 to make our neutral compound. So if we uncross our charges, that's the easiest way to see. Iron would be +3. But there's that algebra that you can do to confirm.
Okay, thank you.
All right, so yeah, we uncross the charges when we want to know, or we uncross the subscripts rather, to make them our charges. Okay, 19, right? We're up to 19. So I think we've looked at beryllium dichloride here in class at least once, right? So if we were to calculate our formal charge here, and I'm not going to draw on all the lone pair electrons if it takes forever, but yeah, so we have, 3 sets of lone pair electrons here on each chlorine. We have no lone pairs on beryllium. But if we calculated our formal charge, we would see that beryllium has a 0 formal charge. We would see that fluorine, they all have 0 formal charges, but it's asking us why we don't form double bonds. So if we tried that, and then we recalculated our formal charge, we would see that chlorine would now have 7 minus 8, right? So chlorine would have a negative formal charge on both of these, right? And where did I get that number from? I did my formal charge calculation where I do valence electrons minus dots plus lines. So chlorine, if I added a double bond, I would have 7 plus 1 for my dots plus lines. So that's where I get the 7 minus 8, the -1. And then beryllium, that should be plus 2 in the end here, right? So we would get positive. Oh, I'm sorry. What am I doing? Backwards here. Because I would take one of these lone pairs. So it would be 7 minus 6. I'm sorry. So chlorine would end up with a positive charge, and the beryllium, we're adding more electrons than it needs for it to be stable. So beryllium ends up with a negative formal charge. So again, valence electrons minus dots plus lines. Beryllium only has 2 valence electrons. It's in group 2. So we would end up with 2 minus 4, and that's where we get that negative. So answer choice D. Whenever you're asked about, is this the best Lewis structure? The answer probably includes something to do with formal charge. Even if you don't calculate it, you can still find the answer choice, including formal charge. All right, let's see here. So we're looking at single bond, double bond, triple bond here, all with the same atoms. So we're really just remembering the trend here that single bonds are the longest and the weakest. Double bonds are somewhere in the middle for both strength and length. Because they have 2 sets of electrons now overlapping, so they get a little tighter, they get a little closer. And then the triple bond is the tightest and the strongest, so the shortest and the strongest. So if we're asked about the single bond here, it will be the weakest and the longest. All right, so that's just kind of memorization, but you can rationalize with how many pairs of electrons are being shared. All right, I'm gonna keep moving. This is like memorization. The electron geometry of blank is tetrahedral. So if we look at all of these central atoms, they all have 4 groups or 4 things bonded to them after we do the Lewis structures. This is phosphine. It looks like this. It's very similar to ammonia, right? Oh, so I have oh, I can't draw it. My 4th electron domain up top there. This is dichloro or dibromo dichloromethane here. So this has 4 things bonded to a central carbon atom. And since we're asked about electron domain geometry, it's just how many groups of electrons, lone pairs, bonding pairs. So as long, I would maybe confirm xenon tetrafluoride if I didn't know that that would be tetrahedral or not. So that's going to be the only one that is not, right? We would think, xenon has 4 bonds minimum, but if we count up our valence, oh, these are all fluorines. We count up all our valence electrons, we would see that it does the expanded octet thing. So it's actually a flat type of molecule. It's not going to be tetrahedral. But all of these others only have those 4 electron domains, so they're all tetrahedral, except for this xenon tetrafluoride. So you would have to confirm, possibly with Lewis structures for this question. All right, and that's a square planar is the proper notation for that. 6 electron groups, 2 lone pairs, 4 bonding for the xenon tetrafluoride. Okay, now we have some more just Lewis dot structure type of problems here. So I can we can do this one kind of from start to finish real quick, right? Just to refresh. So I have BrO3. I'm gonna go to a whiteboard, guys. So we don't so you guys don't have to suffer through me not being able to write. So we're looking for the molecular geometry now of this bromate ion. So again, I'm going to whiteboard here. Okay, so please let me know if you do not see this appear in a moment. It's still loading on my end. All right, so I see some of you moving around, so it looks like some of you have access. Oh, you guys can write too. All right, so I have here, thank you. I have my BrO3 ion here. And so if we were to do our valence electron count, we only have bromine and oxygen. Oxygen's in group 6. There's 3 of those. That gives us 18 valence electrons. Bromine here is at group 7. We have one of those. We'll add those to the mix. So I'm up to 25. I have one extra because it's a negatively charged ion. So that gives me 26. All right. So we have bromine in the middle. We're going to kind of like float around the 3 oxygens here. Oh, I ran out of space. There we go. So I've used up 6 electrons. I have 20 left. So I'm going to place 6 on each of my oxygens. 1, 2, 3, 4, 5, 6. All right, believe me, there's 6 on each. So we've used up 18 more. So now we're down to 2. The last 2 will go on the bromine. Everybody is full. The octets are satisfied. There's no reason for bromine to expand its octet. So we would just assume there's some brackets and a negative sign here, but we don't have any double bonds that need to be formed. So this is it. So if we go back to our exam here, we see there's 3 bonding groups, 1 lone pair on our central atom. How do I get out of here? Hold on. Close whiteboard. Here we go. There's like 7 X boxes here. I don't want to press the wrong one. Okay. Because then we would end early. We don't want to end early. All right. So if you remember, the bromine was my central atom. I was surrounded by 3 single bonds to oxygen with a lone pair. So that gives me a trigonal pyramid. So similar to ammonia, right? And H3. So if you remember ammonia, central atom, 3 bonding pairs, 1 lone pair. And we found the similar electron domain geometry like this. And then we saw that 1 lone pair. We would remember, right? This would be a trigonal pyramid. All right, so now we have 2, I guess we have technically 3 central atoms here, but we're asked specifically about the rightmost carbon. So leftmost carbon, we don't care about. The rightmost would be our kind of central atom there that I can't draw an arrow. There we go. So that's our carbon in question here. So let's think for a minute here. We have double bond to oxygen, single bond over here, single bond over here. Remember, each single, double, or triple bond is 1 electron domain. Let's see if I can change color or something here. How about orange? So we have 1, 2, oh, with that double bond there, 3 electron domains coming out of our atom there. So we only need, or we only have 3 electron domains. So that will give us what? A trigonal planar, right? Molecular geometry. Right, so 3 electron domains has that flat kind of geometry bonded to 3 things. All right.
Excuse me.
Mhm.
This is like a really like off-topic question. When I was in the textbook, there were a lot of constants in like that beginning like chapter 6 part. Do we have to memorize those?
So Planck's constant, no, I don't believe you'll need that in calculation. The speed of light, let's see here. Just to be safe, I would know the speed of light. 3 times 10 to the negative, positive 8, rather.
Yeah.
Planck's constant, I think you're safe with not memorizing. Were there others that I'm not? I think that.
If that's the only ones that we're thinking about, then I'm happy with that.
Okay, yeah, from chapter 6, and then there's the gas law constant, the 0.8, 0.08 to 0.06. So what we
Okay.
learned on Monday, that only that one constant you'll need to
Yep.
memorize.
What about
Okay. Thank you.
Oh.
the solving for wavelength? That with that too, I think.
Well, if we don't need Planck's constant, then there's another formula that utilizes the speed of light, lambda, and relates frequency, but it doesn't utilize Planck's constant. So
Okay.
you still may have some type of question, even if the H you don't need to memorize.
Okay, got it.
Yep, there's
Thank
C.
you.
Oh, yeah, that answered everybody. Okay, great. All right. So I can't always see you when I'm in the screen share, so just speak up if I don't see you. H2O. Okay, so this we've done like a billion times now, right? So we have we do our valence electron count. Right, we have 6 from oxygen, 2 more from the hydrogen, so we have 8 valence electrons total. 2 are used in the bonds, 2 more lone pairs on the oxygen. So we end up here with our central atom having 2 bonding, 2 lone pairs, and we know that gives us a bent molecular geometry. The same thing with 2 bonding pairs, 1 lone pair would also be bent. PCl5 has, what do we have? 5 electron domains, right? We would have P, 1, 2, 3, 4, 5 chlorines surrounding it. You get the picture, right? These are all chlorines. Um, and a blank molecular arrangement. So this was the trigonal bipyramid when we have 5 electron domains and they're all bonding. So that's again mainly memorization. So trigonal bipyramid, 5 electron domains, all are bonding groups. So which of these is nonpolar? All right, so I'm looking for a molecule that does not have a lone pair on my central atom. If I did all of these Lewis dot structures, 1, 2, 3, I know, actually all 4 here would require a lone pair on the central atom because we only have 3 bonding groups. So we can really shortcut this one um, down to the fact that we know that we're going to end up with at least something that looks like this because iodine will have a full octet. Fluorine doesn't do double bonds. So if we did the full valence electron count, Lewis dot structure, all of these would end up with a lone pair on our central atom. And boron trifluoride here, if you remember, boron violates the octet because it only needs 6 electrons around it. We could check formal charge, etc., to prove that this is the preferred Lewis structure. But this is going to be nonpolar because we have a symmetric molecule, and each of these bonds, even though they're polar, are pulling away from that central atom with equal magnitude, right? So equal polarity, so they cancel each other out. So we'll go with B for 26 for all those reasons. Right, but mainly check and see if there's a lone pair in the central atom, then it's done. It is a polar molecule at that point. All right, where are we at on time here? We'll keep moving for at least another maybe 8 to 10 minutes, and then I'll stop share, and you guys can ask me specific questions if you'd like, or I'll stop not share. I'll stop recording. So 3 monosulfur fluoride. So monosulfur means there's only 1 sulfur, but we have variations in our number of fluorines here. So of these, how many are polar, right? So let's see here. We would have to do our Lewis structure for each of these to confirm. But I'll give us a hint here that these 2 will end up being polar. We've seen SF6 before in class. So I'll redraw that one quickly. The reason this one is nonpolar, A, it does not have any lone pairs on the central atom. B, it's symmetric. And then we would see with SF2, SF4, that we may have either a lone pair, well, we will have lone pairs or a lone pair on our central atom with either of these. And then we would just confirm that with the Lewis dot structure. But SF6 here, we've seen this, we're familiar with it. We know that due to symmetry, this would be nonpolar. But we're asked for the polar, and we would do our Lewis structures to confirm these 2. Right. All right, so of these guys, only blank is polar. All right, so we know diatomics are never polar. BCl2, we've looked at this in class a little bit as well, and I mentioned how it's similar to CO2, where we have 2 polar bonds, but they're pulling away in equal and opposite directions. So this one's nonpolar as well. Boron trichloride, this is like BF3, but with chlorines. We've just proved that one was nonpolar a short while ago. Central atom with 3 equal polar bonds, no lone pairs. Carbon tetrachloride. This is similar to methane, except we have 4 chlorine bonds surrounding carbon, no expanded octet. So we know that we would just have 4 equal bonds that are all polar that cancel each other out. So we end up with NCl3. We could have looked at this as well and said, okay, I only have three bonding groups here, and my nitrogen will like to have a full octet, so I know I have a lone pair on my central atom. So again, that will be my first kind of perusal. I would look for any central atoms with lone pairs to start. And then I would consider symmetry, polar bonds that cancel out. And then last but not least, we'll look for any of the, like the diatomics there. And we know that they're definitely nonpolar. All right, so now we have molecular geometry of CHF3. So in this case here, we're going to have our central atom. So we're going to have our carbon in the middle. And then we have four things bonded to it. So I have a hydrogen, right? I have 1, 2, 3 fluorines. So in the end, we would see that, all of our lone pair electrons would be there in our Lewis structure, but we would have 4 bonding groups, or 4 electron domains, all are bonding. So that gives us a tetrahedral molecule. And we would definitely see some polarity because these 3 bonds are polar, and this bond is nonpolar, the CH. So tetrahedral and polar for 29. So this here is saying that the central atom needs 1, 2, 3, 4, 5, 6 bonds. So we're looking for something octahedral. And the only one here that we would end up with an octahedral electron domain would be the xenon tetrafluoride. Beryllium only is bonded to 2 things. This is phosphine. We only have 3 bonds, 1 lone pair. Phosphorus pentachloride, that only needs 5 electron domains, so 5 hybrid orbitals. Br3 negative. You could confirm with Lewis dot structure that a central bromine doesn't gain like 2 extra lone pairs. 1, 2, 3, 4. Yeah, well, there's no way that this one could achieve that 6 on a bromine central atom with the number of valence electrons. So we'll cross that one out as well. But xenon, tetrafluoride, we've looked at this earlier, right? When I mentioned how there would end up in the Lewis structure being 2 lone pairs, and we get this kind of square planar molecular geometry that results when we have 6 electron domains, 4 bonding pairs, 2 lone pairs. So again, we need 6 equal degenerate orbitals. So we need the s orbital, we need all 3 p and 2 d to give us that. 31. Let's see here. We have sp2. The sp2 atomic hybrid orbital set accommodates blank electron domains. Right. So we used 1s and 2p orbitals. So we have up to 3, right? 3 electron domains, right? 1s plus 2 from the 2 of the p orbitals involved. We get a total of 3 degenerate or hybrid orbitals. So we could accommodate 3 electron domains, right? Lone pairs or bonding pairs. 32. We just looked at this one right above. This is kind of another way of asking the same question. Blank hybrid orbitals are used for bonding. They're also used for the lone pairs, right? So all of these hybrid orbitals are used either for lone pairs or bonding in the xenon tetrafluoride. So don't be, perturbed or set back if we're asked specifically about bonding. We know with hybrid orbitals, lone pairs, bonding pairs, they all are the same. NH bond and ammonia. All right, so I don't think sigma and pi made it to the exam just because there's so many topics. Let me do a quick scan here before I go into full detail here. I'll give the answer, but somebody have a question? No, I just hear noise. Okay. No, I don't see any specific questions that ask about sigma and pi bonds, so I'll just quickly mention here that every single bond is a sigma bond. So single bonds are sigma. A double bond has a sigma and a pi bond. And then a triple bond is a sigma and 2 pi. So if you know that, moving forward, even for the final, that's all you'll really need to know. So NH bonds are just sigma. One sigma. Hold on. NH bond and ammonia. Hold on. I don't know what's going on with this question here. Let's see. Oh, and no pi bonds. I'm sorry. I'm like, I didn't see that no there. I was like, there's no correct answer. Okay. So no pi bonds involved. All right. So let's do maybe a couple more here. On your exam, the only hybridization that you're going to be asked about will be central atoms. But there's no reason why we couldn't look at this oxygen here and comment on the hybridization of these orbitals. We see that this oxygen has two lone pairs, right? So they'll need an orbital each. And then we have this double bond here, which requires one hybrid orbital. So we have three electron domains. So this guy would be sp2, right? We use the s orbital, 2p, to give us a total of three sp2 hybrid orbitals. So B for 34, 35. Okay, so we're finally getting to the last kind of stuff on gases here. I'll go through as maybe one or two more. So which is false about gases? So we could go through each of these. These will all be true statements. So they spontaneously fill their container. We talked about that. They expand. Non-reacting gas mixtures are homogeneous. So that means that like the air in the room that we're in, we can't tell where the one gas begins, what another type of atom begins. So they're homogeneous as long as they're not reacting. We might see some type of change if they react. The distance between gases are very large compared to the bond distances. So that's saying that the molecules are teeny tiny, they're held together close, but then there's a large space between them. We can compress them because of that reason. So the only thing that we could guess isn't true, because we know the rest of these are definitely true, is that all gases are colorless and odorless at room temperature. I'm sure you smelled some gases that are not odorless at room temperature. So you can know from real life experience that statement's untrue. Let's see, gases and liquids, what's some differences here? 36. Mm. A liquid does not expand to fill its container, right? But we know gases and liquids are both made of molecules. Gases are always mixtures. That's just maybe not a convincing statement in general. Gases may consist of both elements and compounds. Yes, but so can liquids. So the only difference really between them is that a liquid does not expand to fill its container. All right, which is not a unit of pressure, the millimeter. As a unit of length. What do we have here? Pressure and volume. That was Sir Boyle here. So remember all those relationships that we looked at, Charles's law that dealt with temperature and volume, Avogadro's law, right? That has to do with moles. So Boyle here, he related pressure and volume. All right, so let me stop share here. Are there any specific questions, any problems that you guys want me to go through that we looked at, or any of the last remaining 12 or 15 or so that we didn't get to yet? All right, so I'll just kind of hang out here for a second. Oh, I'm sorry, I forgot to stop record. Sorry, guys.